Hello dear students, welcome you all. So in this lecture, I'm going to discuss the next digital modulation technique that is known as QASK or QAM modulation, right? Here QASK stands for Quadrature Amplitude Shift Keying, right? And QAM stands for simply Quadrature Amplitude Modulation, right? It is the same thing. This QASK is also known as a QAM modulation, and this modulation is commonly used in the modern communication devices, whether it is 4G or 5G communication systems, right? So in this entire lecture, I am going to cover this topic, that what is QASK, what is the need of QASK, and how QASK signals are generated, right? So in the earlier lectures, I have discussed about the simple, different shift keying technique. There were ASK, right, FSK, or it is PSK, and then we come to the M.Sc shift keying, SK techniques. So all these techniques has been discussed in the previous lectures. Now the one thing that was common in all those, that was all these signals have the problem of or drawback of noise oblique error, while these signals are transmitted from a transmitter to the receiver. So there is always a probability of the introduction of noise and error in these signals, right? Another problem is the requirement of the bandwidth, right? Bandwidth or channel bandwidth, right? Requirement. So these two problems are the major challenges while handling the digital signals: noise or error and the channel bandwidth requirement, right? We know very well in the simple shift keying technique, that is B.Sc binary amplitude shift keying, or B.Fsk or B.Psk, or even D.Psk, we use only 2 bits, right, 0 and 1 for representing one symbol, right, either 0 or 1. So that's why it is called as a binary amplitude shift keying or binary frequency shift keying. Now if we want to increase the data rate, right, sorry, or bit rate, then we have to improve the increase the number of bits used in representation of a signal. This was also a major problem that I forgot to tell you, that is the data rate. This is also a very big problem with all these except M.Sc with this ASK, simple ASK or BASK, BFSK or BPSK. So the slow data rate is also a disadvantage, but you know very well that we can increase the data rate by increasing the number of bits. For example, we can use 2 bits, 3 bits, 4 bits for representing a symbol, right, or different representing different amplitude levels, frequency levels, or phase levels in the signal. All these things has been discussed in the earlier lecture. But the main problem that arises, if I increases the number of bits in a symbol the modulated signal, right, then there is a very big problem that came into consideration, or that arise. For example, to understand it, let's look at the phasor diagram, or we can say constellation diagram of a simple 16 PSK, right? 16 means it is a M.Sc, right? PSK modulation technique, where M is equal to 16, means we are using 4 bits to represent a symbol or to represent a level. So this is the constellation diagram, or we call it as the phasor diagram. Now if we look at this diagram, if we were using simply 2 bits binary, then we have only two circles there. this one and this one, you can say. If we were using 4, then we have only, if we were using 3 bits, right, then we will have 8 circles only. But when we are using 4 bits, we have these 16 small circles, you can see. So as the number of bits increasing, right, then the number of symbols in the modulated signal also increases, and this circle in this phasor diagram or circle, they are coming close and close to each other, right? You can see here they are very close to each other. Now if I want to go from 4 to 5, right, 5 bits per symbol, then it will become 32 PSK, right? It means there will be these 32 small circles and they will be very, very close to each other. So the one thing that we can do is we can increase the radius of this circle, or simply saying that we can increase the length of the vectors which are representing it in this phasor diagram, right? It is cos of vega ct phasor, and it is a sine of vega ct. I have discussed it in the early lecture also. So if I want to increase the radius of the circle, right, simply the length of the vector will also be increased, right? Now this length of vector r is directly proportional to the transmitted power that is required for the transmission of this signal. Now you must have understood that we can't increase this length arbitrarily or up to any limit, because the requirement of the power transmission will also increase, and it is an undesirable feature, right? So obviously this is a problem when we are increasing the number of bits, number of symbols in the data. These symbols are coming close and close to each other, and when at the end of this entire process we are going to demodulate or decode this signal, there is a high probability that there is an introduction of error. Suppose this symbol is get shifted toward this side due to the presence of various kind of noise or errors in the atmosphere or in the channel. Then suppose it is shifted toward this side and it is now here. It is shifted toward this side and it is now here. Now when at the receiver end, the receiver will decode this signal, it will make a wrong estimation of these two symbols, because these symbols are representing a particular combination of 4 bits. For example, I can say it is 0, 0, 0, 0. It is 0, 0, 0, 1. It is 0, 0, 1, 0, 0, 0, 1, 1, 0, 1, 0, in this way. So when at the receiver end we are going to decode this signal, then obviously when they are shifted due to the disturbance, interference or any kind of noise, then it will be wrongly decoded by the decoder, and it becomes a very big problem. The entire data that has been sent from the transmitter, it is now getting corrupted, or it is getting distorted, right? So this is a very big problem that comes with the M-array modulation techniques, right? Now in order to solve this problem, new kind of modulation techniques were invented, right? These are known as a quadrature amplitude shift keying technique, and the one is simply amplitude phase shift keying technique. Two techniques are there: amplitude phase shift keying technique, and the second is a quadrature amplitude shift keying technique that is I am going to discuss in this lecture. This is the one problem. So I think now it is clear that how the noise or error is introduced in the signal when we are sending M-array, right, signals, whether they are PSK, FSK or ASK, right? Now the second problem that comes with the PSK particularly, that is represented here. Now you can say, right, this is what? This is a high frequency carrier wave. You can see here it is a sinusoidal wave, it is a carrier wave, right? I have represented all the phase angles: 0, 45 degree, 90 degree, right? And this is a phasor diagram again, right? Or we can say constellation diagram. right? All the points are represented on the edge of a circle, right? Sorry. And we are using suppose 3 widths. 3 widths means we will have 8 different levels or symbols. All these are represented here. Now when this 8 different symbols are going to modulate this high frequency carrier wave, they will modulate it, right? The phase of this carrier wave will be changed according to this constellation diagram or phasor diagram, right? Depending upon the input bit stream. If it is 00, no phase change. If it is 001, the phase change according to this diagram, because 001 is at a 45-degree angle in the phasor diagram. So according to that, we will have a change of phase, right? Now you can see here I have represented the some cases of the different symbols. It is 101 symbol, 011, 111 and 101 again. Now you look at this. This was the original high frequency carrier wave that was used in a P.Sc, phase shift keying technique, right? Phase shift keying, once again I am recalling, phase shift keying means we are changing the phase of this wave, right, in accordance with this input bit stream and according to the phasor diagram. Now when we have 101, you can see here it is it means 225-degree change in phase will be there. So 225 is here too, right? So now I have to complete it. It is starting from here, right? You can see A by 2, right? So it is starting, the wave is starting from here now, and it is again arriving at this point during this period, right? You can see here. So this is the wave, carrier wave in this phase represented here. Now suppose the next symbol or the next width stream is 011. 011 means 135-degree. 135 is starting from here. You can see here it is starting from here. So it has to make a complete cycle before the arrival of next. So it is again arriving or reaching at this point. Starting from this point and reaching at this point. Same thing, starting from here, reaching at here. So you can see here now this wave is represented here in both phase and amplitude. Then in the next, one thing that I want to make clear, that the amplitude of the wave is constant in this case, P.Sc modulation. We are not going to change the amplitude. The next one is 111, 315-degree, right? Starting from here, you can see here, starting from here and again arriving at here. Now, I am hopeful that you might have noticed one thing in this diagram, right? The thing is that there are discontinuities from here to here, right? Phase changes abruptly, right? You can see here, right? There is an abrupt change in the phase as we are going from this point to this point, again from here to here. So these abrupt or discontinuous phase changes in the carrier wave, right, they will create noise or distortion. And when this signal is received at the receiver, it becomes very, very difficult to predict the actual phase of these different symbols, because the decoder will simply look at the phase of these different symbols and it will encode them according to the phase. For example, if the received wave is in this phase, it will encode it or decode it as a 011. But suppose when the error is introduced, distortion is introduced, then suppose then at the receiver it is starting at this end, then what? Then and it is terminating at this end, then there will be a change in the phase. Distortion will be introduced. So this is again a very big trouble with the P.Sc modulation, right? Discontinuities in the phase change. So all these problems were addressed. The one problem was with the phase discontinuities arising due to the nature of the P.Sc, and the second is the this one, the lying of all the symbols very close to each other on the phasor or constellation diagram. We can't, increase the distance between these two, symbols in any arbitrary manner, or we can't increase beyond a limit, because it will increase the, radius, this radius, and we know very well, as I have written here, that the length of the vector is directly proportional to the transmitted power, and that is limited, right? We can't go beyond a certain point, right? So due to these two major problems, a new type of modulation technique was invented, that is known as a amplitude phase shift keying. I have written here from P.Sc to A.P.Sc. A.P.Sc stands for a amplitude phase shift keying. Now here I think the thing is very clear, that in A.P.Sc what we are doing, in addition to changing the phase, we are also changing the amplitude. Now the two changes are taking place in the carrier wave. The one is in its phase and the second is in its amplitude. So that's why we are calling it as amplitude phase shift keying, right? And what is the way of doing it? We are simply taking the high frequency carrier wave and modulating it in such a way that its both its phase and amplitude are changed. The one thing that I want to make clear, that A.P.Sc can be analog or can be digital. Similarly, QAM, that I am going to discuss later, that QAM, that can be analog as well as digital. Here we are discussing only digital part. The difference is, I have told you in the earlier lectures, in analog modulation, the signal that is used is in analog format, whereas in digital modulation, the signal or information is in a digital format. So here I was discussing it. So you can see here now what is the way of doing A.P.Sc. Now in A.P.Sc what we can do, we can represent different symbols or different levels on concentric circles. This is the case of 16 A.P.Sc. This was the case of 16 P.Sc, or a simple phase shift keying, or M.Sc phase shift keying, right? So in this circle, all the points in the were represented on the circumference of this circle. But here what we are doing, we are using two concentric circles. This is 1 and this is a 2, right? So 1, 2, 3, 4, 5, 6, 7, 8. 8 symbols are represented in the inner circle and 8 symbols are represented in the outer circle. So total symbols are 16 now. Obviously, these 8 symbols which are on the inner circle, they have a different length of vector or different amplitude, and the outer circle symbols have a different amplitude. That's why we are calling it as a amplitude phase shift keying. Right now, in this way, I can increase the distance between two adjacent symbols. Right, this is the case of 32 A.P.Sc. 5-bit we are using, so obviously we will have 32 symbols. Right, it is represented here. So inner has 4, I think outer has 16, then outer has again 16. So it makes it not 16, but it will be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12, and the inner one has a 4, 1, 2, 3, 4, and the outer one will have a 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 14, 15, 16. 16 plus 12 plus 4, right? So it makes 32, right? 16 outermost, then the central one is 12 and the inner one is 4. So again, you can see the different vectors are used for the representation. They have different amplitude, or the length of the vector is different. So this is A.P.Sc, amplitude phase shift keying technique. What we are doing here, we are representing the different symbols on concentric circles that have a different amplitude or different vector lengths. So this is the one way of increasing the distance or separation between two adjacent symbols. right? Therefore, reducing the chances of error or noise in the received signal. The second technique that is commonly used is QASK, Quadrature Amplitude Shift Keying, and that is commonly known as a QAM, QUAM, that I have called in the beginning. Here you can see QAM, right? So this is the second technique, and it is the most effective technique that we can use. Now, what is QASK? QASK means we are using quadrature. Quadrature means we are using two carrier waves which are in quadrature. Quadrature means 90-degree out of phase. But in this case, we were using only single, carrier wave, right? This is the difference. We are changing the amplitude and phase of that single carrier wave, but here we are using two carrier waves, right? And these two carrier waves are in quadrature, 90-degree out of phase, and then we are changing their phase, right? The rest of the process is same, right? So you can see here the QASK or QAM, combine amplitude and phase shift, right? Many digital signal created using IQ. IQ stands for in phase bit stream, right? In phase, and Q stands for quadrature bit stream. I have explained it in the earlier lecture that the incoming bit stream is separated into two separate components, right? One is in phase and second is a quadrature phase, odd bits and even bits, and then they are modulated by using a two different carrier waves which are in a quadrature, right? Quadrature, right, shifted by 90-degree, two carrier waves, then resulting constellation are shown here, right? So in this case, this particular case, the constellation that we get, they are square. You can see here they are square, but here in this case they were a round shaped, right? Round shaped means the different symbols were lying on a concentric circles, but here we have a different squares. This one the inner square, right, and this one is the outer one. You can see here. So if I increase the bits from 4 to 5, right, then obviously it will become 32 QAM. Then this is the example of 6 bits, 64 QAM. So you can make different squares. This one, then the next one will be this one, right? Right. So you can see here. So in this way, next you will have in this way, right? So you can see now in this QAM modulation, the different symbols or different levels in the constellation diagram or in the phasor diagram, they lie on the square, whereas in that case they were lying on the circumference of that circle, right? So the main advantage of this QAM is that all these are equally separated. This one you can see here, all these symbols are equally separated from each other, right? Which are the adjacent ones. I'm talking about only the adjacent ones. So adjacent ones are these two, these two equally spaced. You can see here. I'm not talking about this, right? So this is the main advantage of this QAM, right? But in this case, they were not equally, because this distance and this is not equal, right? So this is the difference, right? In APSK, right, that I discussed here, the various symbols were lying on the circumference of circle, but here they are lying on a square. So this is the example, and this is the way of producing, right, QAM signals, right? Now you can see here an example of a QAM modulator. You can see here. So the process is very simple. As I told you, we have one input and the second input. These input are basically coming from where? These are coming from a series to parallel converter. This is the input bit stream, right? Then this separate these into two components, right? Series to parallel means odd bit stream, right, and even bit stream are separated, and then they are sent to the product modulator, right? And for modulation we are using two carrier waves which are in a quadrature. One is cos of vega ct, other is sine of vega ct, right? And then after modulation they are sent to the summing circuit, and then we are getting the output, right? So this is the way of doing this quadrature amplitude shift keying, right? This is a QASK modulator, right? One thing that I forgot to tell you, that in this case this product modulator is doing two jobs. One, it is changing the phase of these two carrier waves in accordance with the incoming bit stream. The second thing is also, it is also changing the amplitude. So it is bit different from the P.Sc modulator or M.Sc P.Sc modulator. It is a bit different, right? Here we are changing both the things, phase as well as the amplitude, right? And then after we are getting the output, right? So this is QAM modulator, right? Now here you can see the comparison between simple phase shift keying, then amplitude phase shift keying, and QAM, QASK, that is. So it is 16 P.Sc, right? Simple phase shift keying. All the 16 symbols are lying on the circumference of the circle. I discussed it in the beginning. This is 16 APSK, right? Amplitude phase shift keying. Here we are using concentric circles, right? And this is QAM. You can see here again. You can make them QAM, circles, but actually they are on squares, right? They are lying on a square, right? So this is the difference, right? So I think the concept of QAM or quadrature amplitude shift keying is clear from this entire discussion. Now I am coming to the applications. So as I told you that the main advantage of using APSK or QASK is that a very high bit rate or data transfer rate can be achieved by these two modulation techniques. So APSK, that is amplitude phase shift keying, it is commonly used in satellite communication. Satellites communication, right? Whereas the QSK or QAM, right? QAM, as I told you in the beginning, it is used in all modern communication devices, right? The recently used 5G signals, right? They are based on QAM, right? In these signals, 64 QAM, right, or 256 or 1024 QAM modulation techniques are used, right? So QAM is basically used in all modern communication devices, whereas APSK is used only for the satellite communication, or in that case where there is less distortion or disturbance in the environment. I mean, it is used in the controlled environment, right? When we are sending data, for example, through cables, then we can use APSK, right? But QAM is used in all these communication devices or methods, right? So this is the most advanced way of digital communication, QAM, and it is commonly used, as I told you. So this is all about the QSK or QAM modulation, and in the coming lecture, I will discuss about the one more digital modulation technique, that is M.Sc, minimum shift keying, right? So till then, thank you very much.